Welcome back. Okay, let's dive right into what is honestly a mathematical masterclass on the Adelic Langlands Program. This framework doesn't just solve one of universal algebra's absolute most stubborn open problems. No, it literally rewrites our entire understanding of how abstract math anchors physical reality itself.
So, we have to start with the core obstruction, right? The finite lattice representation problem. The big question is, can every finite lattice be represented as the congruence lattice of a finite algebra? Now, you probably already know this works perfectly for infinite structures, thanks to the Gretzer-Schmidt theorem. But the second you try forcing the algebra to remain strictly finite, boom, you hit a massive roadblock. The math just completely breaks down.
It's all about how we approach the building blocks. In classical attempts, if you try building a finite algebra element by element, the internal dependencies just explode into infinite combinatorial chaos. It's a mess. But the Adelic solution, it's brilliant. It utilizes the Ayahuasca tower, basically a series of discrete p-adic mathematical filters. By leveraging a strong triangle inequality, the system stops phase errors from accumulating and literally flattens that chaos right onto a finite arithmetic sheet.
To really grasp how this works, we're going to hit 6 key areas in our agenda today. Framework comparison, the Adelic representation identity, the Rankin-Selberg lattice identity, emergent 4D Ricci curvature, universal quantum error correction, and finally, we'll tie it all together with the cosmological engine.
All right, Section 1, Framework Comparison. Let's look at the paradigm shift here.
What's absolutely crucial to realize is the fundamental shift in how we have to treat relations. In classical universal algebra, those static discrete orderings inevitably hide combinatorial defects, which, as we know, leads to infinite state space inflation. But the Adelic Langlands program shifts gears entirely to the Cones-Champ-Sidine spectral action. By treating relations not as static elements, but as closed, unramified orbits of an automorphic data stream, we can actually mathematically track those topological defects, and that leads directly to a closed state space collapse. Implementing this requires a very strict 4-step strategy. Step 1, we inject the finite lattice spectrally using a generalized Dirac operator. Step 2, we map it over to the Langlands dual group to extract the local Satake parameters. Then step 3 is the clamp, the J-theory finite clamp, which limits the algebraic rank. And finally, step 4 uses a global functional equation to force the global conductor to equal 1, which mathematically collapses the entire state space right down into a finite algebra. Moving on to Section 2, the Adelic representation identity. This is our first major pillar. Let's actually unpack this first major equation. If you look at the formula for the combinatorial residue, you'll see that the global Langlands mapping mathematically forces any non-representable residue to just vanish identically. But why? Well, it's because the summation of the local conductor exponents, that little f sub p term, is multiplied by the regularized limit of the zeta function. So under strict unramified stability criteria, this limit forces the whole term to 0. It proves the lattice is perfectly isomorphic to a strictly finite algebra. Actually, let's pause on that f sub p term for a second, because it's super important. The local conductor exponent is basically a measure of local ramification. If a combinatorial anomaly tried to break local symmetry and inflate our state space, it would spike this exponent at a specific prime number. But the global functional equation is having none of it. It acts like a giant vice. Because the global conductor is clamped to 1, the system mathematically forbids any local ramification, forcing f sub p to be 0 straight across the board. Okay, Section 3, the Rankin-Selberg lattice identity. Let's see what happens when systems interact. Pillar 2 gets into the physics of interaction. When two distinct algebras interact, their discrete complexes actually lift into cuspidal automorphic representations. The structural bound here is fascinating. The intersecting volume is capped by a normalization constant and the global Rankin-Selberg L-function derivative. When you unwrap that math, it reveals a massive degree n-squared cross-entropy polynomial across the primes. But here's the kicker. It's reined in by the Euler-Mascheroni constant, which acts essentially as a mathematical shock absorber for Archimedean infinity. Physically, what we're looking at is a massive arithmetic squeezing. Picture two competing congruent systems trying to merge. The prime numbers, acting through those local Rankin-Selberg factors, literally squeeze the cross-entropy inward. Algebras just cannot intertwine with some arbitrary mismatch. This immense arithmetic pressure prevents dimensional inflation from just spilling out into the vacuum. This brings us to Section 4, emergent 4D Ricci curvature.
What happens when we push this to the limit? When these interacting fields push those absolute arithmetic limits we just talked about, it fundamentally warps reality. Maximally entangled operations activate local ramification currents at the finite primes. And through the Grothendieck-Riemann-Roch push-forward, which is a mouthful, I know, this internal arithmetic stress maps directly onto the macroscopic metric tensor. It conformally warps the 4D spacetime base space into exactly what we experience as a gravity well. The physics really comes alive here in Pillar 3 with the explicit formula for the emergent 4D Ricci curvature tensor, R mu nu. Focus on that case of A of n term. That is the universal arithmetic stress factor. Because this factor is entirely locked to the network's prime conductors, arithmetic stress physically manifests as localized stress energy. So gravitational curvature is literally the physical expression of a saturated algebraic bound. To put it simply, matter is just maximally compressed arithmetic data. How crazy is that? Moving right along to Section 5, universal quantum error correction. How does the universe protect all this data? The math maps perfectly here. Under Lagos field theory, a universal algebra isn't just some abstract structure sitting in a textbook. It acts as an active quantum error-correcting code. Those congruence relations we've been discussing, they actually serve as the fault-tolerant logic channels, the congruence stabilizers, of a subsystem stabilizer code. The absolute requirement of finite algebraic closure is the exact boundary that prevents logical states from leaking out into infinite combinatorial dimensions. And this creates a literal cosmic defense mechanism via the Sadike congruence syndrome operator. Say a stray physical error tries to forge a non-local bad operation, well, it acts as a local ramification event, which spikes our old friend f sub p. This specific mathematical deformation causes the determinant of the Sadike polynomial to yield a syndrome eigenvalue that does not equal 1, so it instantly flags the exact prime coordinate of the broken relation. Which triggers the final mathematical failsafe, Pillar 4. The Adelic congruence code invariant. This fault-tolerant projection operator is a massive tensor product stretching across all primes and Archimedean infinity. When a syndrome flags an error, the global functional equation instantly clamps the conductor back to n equals 1. This action mathematically crushes those infinite relational loops and completely locks the finite code space, making the universe essentially completely fault-tolerant. Finally, Section 6, the absolute cosmological engine. Let's pull the whole shebang together. Bringing all these equations together reveals a truly grand architecture. The Adelic information network sits right at the center, constantly maintaining a global conductor of n equals 1. It achieves quantum fault tolerance via those Sasaki polynomials, it ensures space-time closure through the finite representation identity, and it limits combinatorial inflation via gravitational curvature. Ultimately, space-time is a globally synchronized arithmetic web held in perfect balance by discrete p-adic codes. I want to leave you with a bit of a provocative thought to ponder. Today, we've walked through the equations that tightly bound algebraic relations and literally manifest as the curvature of spacetime itself. So the next time you drop an object and watch gravity take hold, ask yourself, are you simply watching mass fall, or are you quite literally watching the universe arithmetically prevent a combinatorial anomaly? Keep questioning, keep calculating, and I'll catch you in the next explainer.